Hello everyone, welcome to my channel. You're watching Math Equals Music. In this video, we're going to be talking about molarity and concentration. We're doing some examples you might see in chemistry and aquatic chemistry. Concentration is number density. The mass density of a substance is given by density equals mass over volume, where the units are kilograms per meter cubed. The mass density tells you how packed these molecules are to each other. Something with a high density means that these molecules are really packed close together. Analogously, the population density tells you how packed the number of people are within a certain area. The units are number of people per meter squared. This crowded city is really packed with people and they're trying to move around the city, kind of similar to a really packed high density substance. The idea of concentration is somewhat similar. So here we have different solutions of coffee. This one on the left is a really dark concentrated solution of a cup of coffee. And as we move to the right, they get more and more dilute. They get less concentrated. So this one on the left is very dark. It has a very high concentration of coffee, has a high concentration of caffeine. And then this one on the right has a very low concentration of caffeine. It's more dilute. So the concentration is the number density. It's given by the number of constituents per volume, where the units are in number per meter cubed. So not to be confused with mass density, which is the mass per volume. So the mass density tells you how tightly packed something is, and the number density tells you how many things there are within that certain volume. So these solutions are equally dense. They have the same mass density, but they have different concentrations as we go more and more dilute. This is going to be the main idea for this video. By the way, these are all scalar functions. Mass density, population density, and concentration, they're all scalars as opposed to vectors. The solute dissolves in the solvent to create a solution. The solute can be a number of different things, such as salts, compounds, contaminants. Usually they're chemicals that are going to be dissolving in the solvent. And the solvent is typically water, but it can also be organic or some other liquid. And when you combine the solute and the solute is going to start to dissolve and then create the solution. So the solution can be as small as a beaker or a cup of coffee, as we've just discussed. It can be as large as a tank or a river, or even the ocean itself is a giant solution of all these different solutes of salts and different compounds dissolving in the ocean. The ocean is a giant solution, a giant mixture. We need a scale to try to quantify these. So we're introducing molarity. The molarity of a solution, we're going to use capital M for molarity, is defined as the ratio of the number of moles of solute with respect to the volume of the solution. So a ratio is just a fraction. So therefore we can just simply write this as molarity is moles of solute divided by liters of solution. So we're looking at the moles, the amount of the solute that we put in, divided by the volume of the solution. The assumption is that the solution is homogeneous, which means that it's well mixed. We're assuming that our cup of coffee is nice and evenly mixed. Let's talk about a few conventions for molarity and concentration. The concentration of a solute I is going to be given by C sub I for concentration is equal to N sub I divided by volume, where N is the number of moles of species I and V is the volume of the solution. And as we've just discussed, molarity is defined as the moles of solute divided by the liters of solution. You can think of concentration as the concept and molarity as the units. The convention is to use brackets around the solute to denote the concentration of the solute in molarity. And concentration is an intensive property. That means it does not depend on the volume of the solution. It's going to be the same throughout. Let's do some examples. 1 mole of sodium chloride is added to 1 liter of water. Calculate the concentration of the species in the solution. Try this problem yourself before moving on. Here we have an image of sodium chloride, also known as table salt, NaCl, and here is the ionic lattice of sodium chloride. So these atoms are strongly bounded together in this ionic structure, but when we add it to a volumetric flask, for example, and then we're going to add some water, the water is going to start to dissolve the ionic compound, and then we're going to have a solution until we reach 1000 milliliters or 1 liter of water. So we can write some equations. 1 mole of sodium chloride dissolves into 1 mole of sodium and 1 mole of chloride. This is represented by this equation. This says that NaCl in the solid phase, the S stands for solid, dissociates into 1 mole of Na plus plus 1 mole of chloride. The AQ stands for aqueous, and notice that Na+, the sodium ion, has a positive charge, and chloride, Cl-, has a minus charge. The plus and the minus cancel out, and we have neutral. The moles of sodium ions in the solution is given by N sub Na+, so N stands for the number of moles, and that's just going to be 1 mole of sodium. And the moles of chloride ions in the solution, that's going to be N sub Cl-, the number of moles of chloride. That's also 1 mole of chloride. So the concentration of sodium chloride, so we're going to write brackets around the sodium chloride. That will tell us the concentration. So we have 1 mole of sodium chloride, 1 mole of sodium chloride divided by 1 liter of solution. That's just 1 molar of sodium chloride. The technicality is we have to assume that the sodium chloride dissolves and there are only ions present. Which of the ions are present? Well, first we have the concentration of the sodium ion. So the concentration of sodium ion, the brackets around the sodium ion, is 1 mole of Na+ divided by 1 liter. That's also 1 molar. And the concentration of chloride ion is 1 mole of chloride divided by 1 liter. And those are our answers. Maybe that problem was a little too easy. Try out this one. 0.75 moles of calcium chloride are added to 250 milliliters of water. Calculate the concentration of each species in the solution. Try it first. First, we're going to write the dissociation reaction of calcium chloride, given by CaCl2 in the solid phase dissociates into Ca2+ in the aqueous phase and 2Cl- also in the aqueous phase. So Ca2+, this is the calcium ion, has a positive 2 charge. Notice that cancels out with 2 of the Cl-. 2 plus charges cancel out with 2 minus charges to get neutral. This equation tells us that 1 mole of calcium chloride dissociates into 1 mole of calcium and 2 moles of chloride. So therefore we can calculate the concentration of calcium chloride. Concentration is moles per liter. So we're going to write the concentration of calcium chloride as the number of moles. We have 0.75 moles of calcium chloride divided by 250 milliliters of water. We need to multiply by conversion factor, which is 1000 milliliters per liter, so that we can cancel out milliliters with milliliters and get left with moles per liter. Our answer is 3 molar. Then we can calculate the concentration of calcium, which is the same as calcium chloride, and that's going to be 3 molar. We have the concentration of calcium chloride and calcium ion. Now we need the concentration of chloride ion. So notice that this equation says that 1 mole of calcium chloride dissociates into 1 mole of calcium, but 2 moles of chloride. So we're going to have to do some conversions. So the concentration of chloride in the solution is given by the concentration of chloride, which is going to be the 0.75 moles of calcium chloride divided by the 250 milliliters of water, which we just saw was equivalent to 0.25 liters. Now we have to multiply by 2 moles of chloride per 1 mole of calcium chloride. So this is some stoichiometry you have to see. We can cancel out moles of calcium chloride with moles of calcium chloride. We're left with moles of chloride per liter, and that's going to be the concentration of chloride. Example 3. Calculate the number of moles of a 2-liter solution of 4 molar sodium hydroxide. Try it first before moving on. Sodium hydroxide dissociates into 1 mole of sodium and 1 mole of hydroxide. This is given by this equation, which says NaOH solid sodium hydroxide dissociates into 1 mole of Na+ in the aqueous phase and 1 mole of hydroxide in the aqueous phase. We want to calculate the number of moles. So we have the concentration of sodium hydroxide, that's 4 molar, and we want to solve for the moles of sodium hydroxide. So if we know the molarity and we know the volume, we can multiply those by this equation, calculate the moles. The moles of sodium hydroxide is going to be given by N sub NaOH, the moles of sodium hydroxide, is going to be the concentration of sodium hydroxide times the volume of the solution. Concentration again is 4 molar. I'm going to multiply by the volume of the solution, which is 2 liters. Instead of writing it as 4 molar, I want you to write it as 4 moles per liter so that we can cancel out liters with liters. We'll get moles. Our answer is 8 moles. Example 4. How many milliliters of 1.5 molar KOH are needed to provide 0.125 moles of KOH? try it first. So if molarity is moles per liter, and we want to solve for how many milliliters, I'm going to multiply both sides by liters. We're going to cancel out this liters, and then I'm going to divide both sides by molarity. So I can cancel out this molarity and this molarity. In other words, we have the volume of the solution is moles divided by molarity. So we know 1.5 molar and 0.125 moles. We're going to plug in the equation. We have the moles divided by the concentration, which is 0.125 moles divided by 1.5 moles per liter. Again, write it as moles per liter instead of just molarity. And so that way we can cancel out moles and moles. But what's going to happen to this liters? Well, let's do a side note we might recall from algebra. If we have a fraction divided by a fraction, a over b divided by c over d, well, we're going to know that this denominator goes all the way to the top, so that way we can multiply a times d and divide it by these two in the denominator, b times c. So a over b divided by c over d is equal to a times d divided by b times c. In other words, this liter is going to go all the way to the top in the numerator, and then we can multiply these out. So we get our volume is going to be 0.125 liters divided by 1.5 times the conversion factor, so we can cancel out liters. Our final answer is 83.3 milliliters. One more example, example 5. A 500 milliliter solution of 1 molar hydrochloric acid is prepared. 1 milliliter aliquot of this solution is extracted. What is the concentration of the aliquot? All this is saying is, suppose we have a beaker and has a certain concentration of hydrochloric acid, 1 molar, and the volume is about 500 milliliters. And we're going to take a 1 milliliter aliquot. An aliquot is just simply, we're going to take our pipette and we're going to extract a little bit of that solution. So 1 milliliter is extracted. That's our aliquot. The concentration is an intensive property, meaning that the concentration in the entire solution should be the same, right? And it's homogeneous. So assuming the solution is homogeneous, the concentration of the aliquot is the same as the concentration of the solution. There's no reason that the concentration we extracted is going to be any different than the concentration of the solution. Therefore, the concentration is the same, 1 molar hydrochloric acid. To recap, we said that concentration, an intensive property, is a scalar function defined as the ratio of the number of constituents with respect to the volume of a homogeneous solution. So this is my complete definition for concentration. We said that concentration is an intensive property, which means that it doesn't depend on the volume of the solution. It's a scalar function as opposed to a vector function, and it's defined as the ratio of the number of moles, the number of constituents, divided by the volume of the solution, and it has to be homogeneous. It has to be a well-mixed solution. As an equation, we have the concentration of species I is the number of moles of I divided by the volume of the solution, or quite simply put, we define molarity as the moles of solute divided by the liters of solution. If we want to solve for the number of moles, we're going to multiply the concentration by the volume. If we want to solve for the volume, we're going to divide the number of moles by the concentration. If you want to understand this, rather than memorizing this page, I recommend you practice. Do many different combinations of solutes and solutions and try to calculate the concentrations, moles, or the volumes. These are the sources I've used to make this video. I recommend you check out some simulations to understand the concept of concentration. That's what I used in high school. That's it for this video. Please subscribe to my channel, whether you're on YouTube, Instagram, or TikTok. Let me know what kind of problems you'd like to see next.